Clothing makes up an integral part of everyday life and has done so for many millennia. But have you ever wondered about the materials they are made of, what impact they are having on the environment, or what the future holds for clothing? To answer these questions, we first need to understand the science behind our clothes. The basic building blocks of any textile structures are fibres. All fibres are polymers. The Oxford English Dictionary defines a polymer as a compound with a molecular structure in which a large number of polyatomic units are bonded together. In other words, a polymer is a large molecule which is made up of small repeating units called monomers. Polymers are described as being either homopolymers, when they contain only one type of monomer, or copolymers, that are made of two or more monomers. The word polymer originates from the ancient Greek word polymeres, poly meaning many and meres meaning part. It is first thought to have been introduced in 1833 by the Swedish chemist Jöns Jacob Berzelius, but not with the modern meaning. It was used to describe molecules that had identical empirical formulae but very different chemical and physical properties. In the 1920s, the German scientist Hermann Staudinger proposed a definition that we would now associate with polymers. He described a polymer as small monomer units joining together to form large molecules in his work on macromolecules. For his work, Staudinger won the Nobel Prize for Chemistry in 1953. Nowadays, the word macromolecule is used interchangeably with the word polymer. Polymers can be classified in a number of different ways. They can be categorized as either thermoplastics or thermosets, depending on their response to thermal treatment. Thermoplastic polymers melt when heated and re-solidify when cooled, whereas thermosets do not melt when heated, but at high enough temperatures they will decompose irreversibly. Another classification system is to categorize polymers depending on how they react. In 1929, the American chemist Wallace Carothers suggested that polymers should be categorized as either condensation or addition polymers. Condensation polymers release a small molecules such as water or hydrogen chloride when formed. Addition polymers are those formed from addition reactions of unsaturated monomers. Another American chemist, P.J. Flory, slightly modified his categorization to polymerization reactions being either step growth or chain growth, instead of condensation or addition. One of the main differences is that on the synthesis of polyurethanes via step growth polymerization, there is no elimination of a small molecule. Chain growth polymerization leads to the production of polymers by monomers adding to the chain one by one. There are multiple methods of carrying out chain growth polymerization, including organometallic catalysis and ring opening metathesis, but the three main methods are free radical, cationic, and anionic polymerizations. All of the different methods have the same basic three-step process: initiation, where a reactive species is formed and reacts with the first monomer to produce a reactive polymer end group; propagation, where the reactive end group reacts with more monomers, extending the chain length; and finally, termination, where something happens to stop the polymerization reaction by deactivating a reactive end group. Chain growth polymerization reactions form polyolefins. Polychloroethene, also known as polyvinyl chloride or PVC for short, is a common example of a chain growth polymer. It undergoes a free radical polymerization reaction. A free radical is a species with an unpaired electron. In initiation, a peroxide is used as the initiator. It is activated by breaking the weak oxygen to oxygen bond using either irradiation with ultraviolet light or heating to produce two alkoxy free radicals. The alkoxy free radical is very reactive and will attack one of the chloroethene monomers present in the reaction vessel, forming a reactive radical monomer. During propagation, the reactive radical monomer goes on to attack another chloroethene monomer, which adds to the chain and moves the reactive radical to the end. This continues with monomers added to the reactive polymer chain one by one, extending the chain and moving the reactive species to the end. Termination stops the propagation process by quenching the reactive radical species. There are two main termination processes: chain combination, where two reactive polymer chains join together, and disproportionation, where a proton is abstracted from one of the polymer chains, leading to the formation of one alkane and one alkene polymer. Cationic and anionic polymerization reactions follow very similar processes, however they have different initiators. The cationic process uses Lewis acids, and the anionic process uses strong nucleophiles such as butyl lithium. They also form different types of reactive end groups. The cationic process has a cation, a positively charged ion, and the anionic process has an anion, a negatively charged ion. In step growth polymerization, all of the monomers are active, meaning that they can form oligomers, which are small chains of monomers. As the reaction progresses, the polymer chain length slowly increases due to these small oligomers combining with one another. The monomers in step growth polymerization must have reactive functional groups, such as a carboxylic acid or an amine. Step growth polymerization reactions form polyesters, polyamides, polyurethanes, epoxy resins, silicones, and polyethers. Nylon 6,6 is the most common form of nylon. Nylon is not just a single substance but a family of very similar materials. They are all polyamides formed from a step growth polymerization reaction of dicarboxylic acids and diamines. Nylon 6,6 is formed from a step growth polymerization reaction of adipic acid and hexamethyldiamine. In the first step of the mechanism, two adipic acid monomers react with one another, with one protonase in the other. This protonated monomer then goes on to react with a hexamethyldiamine monomer. The lone pair on one of the nitrogen atoms attacks the carbonyl-carbon to produce an ammonium intermediate. In the ammonium intermediate, the oxygen steals a hydrogen from the nitrogen atom to form an amide dimer, expelling water and a proton. The dimer can then go on to react with other oligomers to form larger oligomers, which in turn can react with other oligomers to form even bigger oligomers. This process continues and forms the polymer nylon 6,6. Clothing has been used for many millennia, with the use of textiles from natural fibres dating back as far as 4000 BC. Throughout history, the fibres used in the production of clothing has evolved with new materials, production methods, and technologies being created. It is only in the last 100 or so years that clothing production has had many developments. The first major breakthrough was in 1892 when artificial silk, now known as rayon, was created from the natural polymer cellulose by de Chardonnay. This was the origin of man-made fibres. Since then there has been many advancements in the man-made materials used in clothing. In 1939, DuPont developed the well-known material nylon. The early 1940s saw ICI's development of polyethylene terephthalate, PET for short, and in 1958, DuPont formed the successful, and not always so flattering, spandex, also known as lycra, from segmented polyurethane. All natural man-made fibres are polymers. Natural fibres are formed through a biological process which determines the form and structure of the fibre. Man-made fibres are classified into two different groups: synthetic and regenerative fibres. Synthetic fibres are completely synthesized by man, from the starting material to the final fibre form, whereas regenerative fibres are not true synthetic fibres. They use natural polymers as a starting material, which are converted into the form of a fibre or regenerated into the shape of a fibre via a physiochemical process. For example, rayon is made from purified cellulose derived from the wood pulp from pine, spruce or hemlock trees, or cotton linters. There are numerous polymers which make up the clothing that we wear. In the modern clothing market, the two most dominant polymers are polyester and cotton, with polyester making up 55% of total production and cotton 27%. Synthetic fibres make up approximately two-thirds of the clothing market. They include polyester 55%, nylon 5%, acrylic 2%, and spandex, which only makes up a small volume of the polymers in clothing, but is used in small quantities in lots of them. Cellulose-based fibres, or plant-based fibres, account for approximately one-third of all the polymers used in textiles. They include cotton 27%, rayon, lyocell, and bast fibres such as linen, hemp, and jute. Protein-based fibres are fibres from animal sources. They correspond to less than 2% of all fibres used. The vast majority of this is wool, but silk is also a common protein-based fibre. Man-made fibres have many advantages over natural fibres, such as their high strength, durability, dimensional stability, resistance to bacteria and insects, no demand on fertile land, and they can have their properties engineered. Some advantages natural fibres have over man-made fibres are their comfort, being environmentally friendly, elegance, and being safe to use. The clothing industry has the fourth largest environmental impact after housing, transport, and food. This is mainly due to the ever-growing culture of fast fashion. Fast fashion was a term coined in the 1990s to describe the trends that move rapidly from the catwalk onto our high streets at breakneck speed. In 2015, the production of textiles totaled in 1.2 billion tons of carbon dioxide equivalent being emitted. To put this into perspective, this is more than the emissions by all international flights and maritime shipping combined. This is partly to do with the ever-rising use of synthetic fibres. For example, polyester, the most abundant fibre, produces almost 3 times the amount of carbon dioxide equivalent to cotton in its lifetime. A polyester t-shirt creates emissions of 5.5 kilograms of carbon dioxide equivalent, whereas one made from cotton releases only 2.1 kilograms. However, greenhouse gas emissions is not the only environmental impact that the clothing industry has. It also uses up vast quantities of our vital resources. In 2016, the consumption of water for the production of clothing was 8 billion meters cubed. Globally, the average consumption of water for 1 kilogram of cotton, equivalent to one man's shirt and a pair of jeans, is 10,000 to 20,000 litres. Cotton production accounts for 69% of the water consumption of the clothing industry. Water consumption is not the only impact the clothing industry has on water. 20% of freshwater pollution is reported to come from the treatment and dyeing of textiles. In addition, the clothing industry relies on the use of non-renewable resources such as oil to produce synthetic fibres, fertilizers to grow cotton, and chemicals to produce dye and finish the textiles. This accounts for 98 million tons of resources every year. The cotton industry alone uses huge quantities of pesticides and insecticides, accounting for 6% of global pesticides and 16% of insecticides, despite only covering 2.4% of the world's cultivated land. The clothing industry produces approximately 500,000 tons of plastic microfibers each year. A microfiber is a type of microplastic, a particle of plastic smaller than 5 millimeters. They are released into the oceans when clothing is washed and has been found in the extremities of our planet, such as the Arctic and Antarctic. The amount of plastic microfibers produced each year is equivalent to that of more than 50 billion plastic bottles. Despite the negative impact that the clothing industry is having, the future is looking brighter. There are currently lots of schemes in place, not only to decrease the impacts of the clothing industry, but also to educate about the damage it is currently having. In the last few years, there has been huge advancements in lowering the impacts of the clothing industry. For example, many high street brands have begun to introduce collections of clothes that are more environmentally friendly, such as New Look Kind, Boohoo for the Future, Levi Waterless, H&M Conscious, ASOS Eco Edit, and Marks & Spencer's The Cotton Edit. More recently, there has also been huge advancements in technologies to produce environmentally friendly polymers. One such example is that in 2019, Adidas by Stella McCartney released 2 new products, both of which were in partnerships with companies at the forefront of research and production of environmentally friendly fibres. The products were the Biofabric tennis dress, created with microsilk and cellulose blended yarn in collaboration with Bolt Threads, and the Infinite hoodie, which uses new cycle fibres by Evernew. The Biofabric tennis dress is the first of its kind, using a cellulose blended yarn and microsilk. Microsilk is a protein-based material that is based on fibres produced in nature, such as the fibre produced by spiders, and uses renewable ingredients like water, sugar and yeast. This therefore means that it has the ability to fully biodegrade at the end of its life. The Infinite hoodie is a 100% recyclable hoodie from clothing waste using new cycle fibres. The hoodie consists of 60% new cycle fibres and 40% organic cotton fibres that have been diverted from landfill. The new cycle fibres are made from disregarded clothing. The textiles are diverted from landfill, collected and separated. Evernew uses a chemical-based process to prevent the weakening of the fibre and breaks the cotton down to its original building blocks. Once these building blocks have been extracted, as a liquid pulp, they are spun into new yarns which have unique performance advantages. The new cycle yarn is then combined with organic cotton to create a stronger and more durable product than the starting material. The Infinite hoodie was an ultra-limited run of 50, all of which were given to athletes, but Evernew is hoping to commercialise in the near future. Engineers and scientists working in polymers and textiles will be important in the future development of sustainable fibres as our concerns of the impact of climate change increase.